Okay, so exponential functions. This next thing is kind of a cool proverb. Have you heard about this? It was, I think that the original story was in terms of grains of sand. Okay, so what job do you want? Do you want the job that gives you $1 million at the end of the month? Or it gives you 1 cent the first day, 2 cents the next, then 4 cents, then 8, etc., and it doubles every day. And okay, so I want you seriously, who votes for A? Like, does anybody can vote for A? Who's gonna vote for B? Is that because you've seen this before and you know what happens with exponential growth? Okay. So, huh? We're gonna say it's worst case scenario and it's February and it's not a leap year. Okay, did we change their mind? We don't know. Okay.
28.
Okay, so 28 days. So on day 1, you get paid 1 cent, right? On day 2, you get paid 2 cents, right? Day 3, you get paid 4 cents, right? So that's 2 to the second, 2 to the first. On day 28, you get paid how much? 2 to the, what would the power be? 27. Does that make sense? And that's cents. So just FYI, 2 to the 27th is actually not approximately, it's actually equal to 134217728. And that's still in cents, okay? So dollars, good. And put your commas in. You get paid more than $1 million on the last day alone. Not to mention the day before it. Does that make sense? That's an example of exponential growth, right? The growth just blows up. I've known these math professors here at UAF for a long time because I went to grad school here, and so some of them have kids, and one of their kids wanted to like make the computer count to 1 million, I think it was, and it would take way too long counting by ones, and the dad's like, oh, we'll make it count by twos, count by powers of 2, and it does really quickly. So. But there you go. Maybe it was 1 billion. It might have been a bigger number than 1 million, but it was huge. So that's an example of exponential growth. So the first thing you have to know pretty well in this class are these basic rules for exponents. So what happens when you multiply things that have a common base? Like if you did, say, I don't know, a squared times a cubed, what happens to the exponents? Oh my God, no, they don't multiply. They add, there we go. So this is b to the x plus y. And that's just the basic definition. A squared is a twice, a cubed is a 3 times, right? Hence a to the 5, right? A, right? Okay. When you multiply exponents add, what happens when you divide? They subtract. What happens if you multiply? So think for a second. A squared cubed means a squared 3 times, right? Which is how many a's? A to the 6. What happened to the numbers? They multiplied. So in this case, they multiply. And this last property is just saying, like, what if you had, say, 2a and you cubed it? If you do 2a times 2a times 2a, both the 2 is cubed and the a is cubed, right? Yep, and the fancy way to say that correctly is the power distributes over multiplication. Versus a plus b to the x is not equal to a to the x plus b to the x. We discussed that yesterday, right? Powers distribute over multiplication. That's a fancy way of saying the operation inside the parentheses is multiplication. Versus over addition is not true. And you can prove that to yourself pretty quickly by just figuring out that a plus b squared is not equal to a squared plus b squared. I'm pretty sure the only power that's true for is a power of 1, which is kind of stupid. Maybe it's true for a power of 0 as well. And one more thing, let's add in really quickly, add in an e, because this one's going to come up. What if you have something to a negative power? You punish it and send it in the basement. 1 over b to the x. You Lilo and Stitch it. Okay. Oh, and one more, add an f. What is stuff to the 0 power? 1. this rule and the subtraction rule are the reason that e is true. Like if I take 1 over b to the x, that's b to the 0 over b to the x, and 0 minus x is negative x, right? Okay, so there you go, summary rules. These rules are true with weird stuff like the things you're going to see next. If you have e to the 5x squared, what happens to those powers? They multiply, and that becomes e to the 10x. Notice it's not e to the 25x squared, right? It's e to the 10x. How about this one? What happens to those? They add e to the 2 plus x. And how about this one? Subtract 5 to the 2 minus x. Does that make sense? So those rules apply to other weird stuff. I mean, if I said, for example, e to the x to the power of x, what would that be? Do the exponents multiply or add? Multiply. E to the x squared, right? Versus e to the x times e to the x, that's e to the 2x, x plus x. You've got to think about those rules really abstractly. Does that make sense? Okay. And that's often something that doesn't come up in pre-calc books enough, so it's good to kind of review it quick. Okay. I think we briefly discussed what like e to the x looks like as a picture. Let's talk about what 2 to the x looks like as a picture. Your backup fallback method is 2 plot points, right? Okay, so plug in numbers. Plug in 0, you get 2 to the 0 is 1. Plug in 1, you get 2. Plug in 2, you get 4. Plug in 3, you're going to get 8, etc. Okay, so there's the growth of your cents over your pay period. What happens when you plug in negatives, like negative 1? 2 to the negative 1 is 1/2. And then a quarter, and etc. Okay. So those numbers will never get to 0, but they get close to 0. The domain of this function is minus infinity to infinity, or all real numbers. The range is 0 to infinity, but does not include 0 because you never get all the way there. Okay, does that make sense? What's 1 to the x going to look like? It's going to be a straight line. 1 to any power is 1, right? So that will be a straight line, kind of a stupid function. You buy that? Does that make sense? Like 1 squared is 1, 2, 1 squared, 1 to the 5th is 1. 1 to the negative 1 is 1 over 1, still 1, right? Okay, so that one's dumb. Yeah. 1/2 to the x. Now this one I think instead of plugging in numbers, I'm going to show you a little trick, okay? 1/2 is the same thing as 2 to the negative 1st. Do you believe that? Yes? Okay, what happens to those exponents? They multiply. So that becomes 2 to the negative x. So this is 2 to the x reflected over which axis? It's inside the function, right? Over the y-axis. Does that make sense? Okay. What would it have had to have been for it to be reflection over the x-axis? It would have been a negative here, and this would have been positive, right? Okay. So this picture, take your picture from A, and instead of increasing, it's going to decrease. Have you guys heard of exponential growth and decay? Or half-lives and things like that in chemistry? The first one that we did in example A is an example of exponential growth, right? This is decay. Specifically, the part A is actually doubling. This one is halving or half-lifing. Alrighty. Perfect. The nice thing about 2 to the x versus e to the x is 2 to the x goes through some nice points. E to the x only goes through one nice point. Okay. So how would you graph this function? What is your parent function? And then you flip it over which axis? And then move it up or down? Up 5. Okay, so there's the parent function. There's its reflected child. And somebody made their parents happy and actually gave them grandchildren. That was a stab at myself because my parents would like me to have kids. Sorry, TMI. Okay. Okay, all right, there you go. The blue thing is your final picture. And if your function has an asymptote, you should draw it in. And if it goes through some easy points, you should draw those in too. I gave you grids, put the dots in the right places. What is the domain of this function? I'm going to be lazy and use that R symbol because it's less writing, if that's okay with you. What is the range? Negative infinity up to 5. Does it actually hit 5? So you get a parenthesis there. Does that make sense? So you don't actually have a point that actually crosses that axis. If you do, it should be pretty obvious. Does that make sense? Like the root function obviously has a stopping point, as opposed to an asymptote it approaches. It's because it's positive 5. It never touches the 0, exactly. It never touches the 0 line either. And that's if it doesn't touch the 0 line, it doesn't touch whatever line it's gotten moved to either. Exactly. Okay. So finding exponential functions is using the fact that all exponential functions are something of this form. And there are lots of ways to write them equivalently, but one thing to remember is that kind of like lines are y equals mx plus b. Yeah?
Quick question. Do you want us to label our asymptotes?
You don't have to put in like y equals whatever, but just draw them in the picture. If I asked for them like labeled, I'd like give up space for you to like write the equation or something. Good question though. So this is the general form of an exponential function, and just kind of like lines are y equals mx plus b, right? Exponentials have that a coefficient not raised to a power plus something to a power, and it goes through these 2 points, and those 2 points are x's and y's, right? So can't you kind of like say, okay, well if that's true, I know 6 equals a times b to the first. Does that make sense? Because you have the point 1, 6, x is 1, y is 6. You know it's exponential, so it's a times b to a power. So 6 equals ab, and you're like, okay, I'll save that for later. What else do you know? 24 equals a times b to the third. So given these 2 equations, can you somehow put them together and find a and b? Any ideas? Specifically, I was thinking something to the effect of a equals 6 over b. Does that make sense? Do you agree with that? No one's looking very happy. A, then that can go in for the a. 24 equals 6 over b times b cubed. 24 equals 6b squared. Do you buy that? What next? 5 by 6, okay. Technically, you get b as plus or minus 2. Completely technically. But bases and exponential functions can never be negative. And the reason is they're not defined for all numbers then. Like, think about taking negative 2 to the 1/2 power. That makes imaginary numbers, right? You can't square root negatives, right? 1/2 power is a square root. So this is just, your base is 2. And then what does the a have to be? Because you know this is true, right? A has to be 3. So the exponential equation is 3 times 2 to the x. So lines have m's and b's. Exponential functions have a coefficient and a base. Boo. Okay. The other kind of good thing to know is how to set up equations for doubling things and half-lives. We did this a little bit in my pre-calc class, and hopefully you did too. So your bacteria culture begins with 1,000 bacteria and doubles every 3 hours. Think Contagion. Have you guys seen that movie? Don't watch it, it's super scary. Okay. Okay, so at time, and then we'll say amount. Let's make a little table and see if we can find the pattern. So at time 0, which is when you start, how many bacteria do you have? 1,000. After what time has it doubled? 3. It is at 2,000, right? Okay, what's the next time you would know something about pretty easily at time? 6, it'd be 4,000. 9, you'd be at 8. And by 12, you're at 16,000, right? I asked about time 11, and time 11 isn't like a nice one that you can just get from the table, or just from going by 3s, right? Okay, so here's how you can make this in. You could do an equation thing like we just did, but you can also get it by thinking about it. So this number, you start with 1,000, right? You want to multiply it by 2 to some power. I'll just call it t for now. Actually, okay, well, I'll do it this way, I'll do it the other way too. But when you plug in t equals 1, does it give it the values in this table that we're supposed to have? If you plug in 1, you would get 2,000 at time 1, right? So you'd be plugging in 1 when the time is 3, so that actually should be t over 3. And this is a general form for equations that are, generally speaking, doubling time. This is always how much you start with. And this ends up being the length of doubling time.
So if it was every 4 hours, it'd be t over 4?
Mm-hmm. You can actually find that the other way too. Like if you start with this a times b to the x thing, it will also work. It's like, for example, you plug in 0 for x. We probably should have made it t, but whatever, I'll make it a t. Okay, a times b to the t. If t is equal to 0, you have 1,000 equals a times b to the 0, which tells you that a is equal to 1,000, right? That part we got. Yes? Okay. Then you're like, okay, well, I'm going to use that. I know I've got 1,000 times b to the t. What could you plug in next? What could go in for t next, for example? Come on. What's this next point? What's t equal to? 3. And the a is going to be 2,000. B to the 3rd. Okay. Divide by 1,000 and you get 2 equals b cubed, right? So how do you undo that cubed? So b is the cube root of 2, okay? You guys agree with that analysis? Okay, that's the same thing as the equation a equals 1,000 times the cube root of 2 to the t power. Okay, there's your equation. And the question is how does that match what we had before? what is an alternative way to express the cube root of 2 as 2 to a power? 2 to the 1/3, exactly. And so then what happens to those powers? They multiply and you get the same thing. So if you forget the other way, that's how you could figure it out. And I probably wouldn't count you off if you like left it as this, right, and didn't do the last thing, but it's good to know that that's how things work. So it's exponent rules very generally again. Okay, so awesome. Oh, I said something about figuring out when it's going to be, how many they're going to be after 11 hours. How would you figure that out? A of 11 will be, so 1,000 times 2 to the 11 over 3. Some of your homework questions like this one really do involve a calculator. On the quiz, I'll just make it nicer. You'll just leave it like that. It's approximately 12,699, right? Okay. I'm going to do the last part. I think, did you guys run out of space? Okay, a little bit. We'll skip the last part that says, can you figure out when the population is going to reach 10,000? Because we're going to do it in the next example with a different question. I should have made myself A's, B's, and C's so I could keep track that I'd actually answered everything that was asked there. Okay, so next one, same idea except for its half-lives. So here's my chemistry. The half-life of a strontium-90 is 25 years, meaning half of any given quantity is going to disintegrate in 25 years. So if your sample has 100 milligrams to start, give me an expression for the mass after t years. When you double, we repeatedly multiply by 1/2, right? When you half, what do you repeatedly multiply by? Like you'd say you start with 100, then you're going to half it, and half it again, right? Halving involves either division by 2 or multiplying by 1/2. Same idea, right? So this equation will be how much you begin with times 1/2. And kind of how that other power ended up being t divided by doubling time, this will be t divided by half-life, which is 25. And you can think, because then when you plug in 25, you do 100 times 1/2. When you plug in 50, how many half-lives have gone? 2. So you plug in 50 and you get this exponent is 2 multiplied by 1/2 twice. So, okay, how much after 40 and 80 years? So you plug in 40. Make sure you put parentheses where I put them when you put that in a calculator. So otherwise it'll do that 1 after the 40th and then divide it by 25 as opposed to putting the whole thing in the exponent. Okay? That's approximately 32.988 milligrams, I think it was. Yep.
These are all calculator problems, so.
Oh gosh, yeah. Yeah.
Would we just leave it at the power of 40
Yep.
/ 25?
Yep. If it was on a quiz, I would just say leave it, you know, or what I might make you do in a quiz is just get me the equation and I would assume that you can do the rest of it. Because if you can do this, I'm pretty sure you probably can plug numbers in correctly, right?
Oh, yeah.
So,
If we have that fraction, could we make it into a decimal, like 40 over 25 is 1.6, or?
yeah, but the still working it out would be kind of tricky, like without a calculator. But you could make it 1.6 and put it in the calculator that way, that'd be totally fine.
It'd be easier.
It also would be easier, yep. This is about 10.882. Okay. So part C is the part that actually involves a little bit of more algebra. Estimate the time required for the mass to be reduced to 5 milligrams. So how is that question just a tad bit different? Plug 5 in for the M. And this will involve you remembering a little bit more than I've reviewed thus far because I'm going to actually solve this algebraically as opposed to graphing. So on your written homework for this lesson, the book says on 2 of the questions in part D to estimate by graphing. I think I wrote in there, don't use graphing, just solve them using algebra like I'm going to show you now. Okay? So to get the t by itself, what's the first thing that you could do? Divide by 100. And I think 5 over 100 is 1 over 20. Okay. So 1 over 20 is 1/2 to the t over 25. And you guys are supposed to have had pre-calculus or algebra at some point in time in your lives. There is a function whose job in life it is to take powers out of powers. What is that function? Some kind of logarithm. So I'm going to use the logarithm ln, which we're going to formally review in the next section, okay? You apply this ln function to both sides, and one of the properties that it has is it takes powers and makes them coefficients. That is ln's purpose in life. It has to do its job. So that power of t over 25 becomes t over 25 times ln of 1/2. And that's something that your textbook didn't assume that you can do, but because I'm going to teach it to you today, I'm going to assume that you can actually do it on this lesson. And then how could you get the t by itself? I'm going to multiply by 25, because the 25 is actually in the denominator. Does that make sense? And then divide by the ln of 1/2. So t will equal 25 ln of 1 over 20 over ln of 1/2. And if it's a test question, that's where I ask you to stop. If it's a homework question, take out your calculator, and it's approximately, my work says 25 years, and I know that's wrong. What do you guys get for that? Because somebody doesn't mind punching the buttons. Did you get it, Chris?
108.048.
So I had to cough when you were speaking. Sorry, it was 100 and...
108.048. I didn't check it though.
I think that seems reasonable, though, right? If it's 25 years, 5 milligrams is an awfully long time, right? Yeah, same thing? Okay. There's no rule that says ln is the best function. There's also a function called log that does the same thing. It's just you've got to push the right button. And if you used logs, which is log base 10, instead of ln's in that last expression that I wrote, you're going to get the exact same answer. Okay. So, is everyone all right with that? Okay. All right, the number e. So we discussed briefly yesterday that e is a special number, and e is this irrational number, and e is approximately equal to 2.71 and then some stuff, right? It's one of those irrational things that doesn't repeat, doesn't end, etc. Do you guys remember how pi is defined? It's the circumference divided by the diameter of a circle, right? That's where that pi number came from. Here's where the e number comes from. E is equal to the limit as n goes to infinity of 1 plus 1 over n to the power of n. So what that means is if you take 1 plus 1 over n to the n and plug in huge n's, you get close to 2.71, etc. Proving that that number is irrational requires a lot of work and a lot of math that you guys don't know yet. But that's the general idea of where this number comes from, sort of in just stuff. Kind of like pi was sort of found to be this ratio, it's true about circumferences divided by diameters in circles. This is where that e number comes from. And it's kind of weird because if you think about this, if n gets large, it's kind of like 1 plus 0 to the infinity power, right? And you think 1 to any power is 1, but it turns out it matters how quickly this goes to 0 and how quickly that goes to infinity, which means it's not actually 1. We'll learn how to find limits like that in this class. Okay, so that's e's definition. We kind of already discussed this, but what does the function e to the x look like? Just be able to graph it. It's kind of like 2 to the x, right? What's one nice point it goes through? And then 1 and 2.7-ish. So there's e to the x. What does doing 2e to the x, what does that 2 do to all of the y values? So the one that was 1 becomes 2. The one that was 2.71 becomes 5.4-ish, yep. Okay. But it still retains the same general shape, right? And then what does this negative do, and what does that plus 5 do?
Flips it on the y.
And then moves it
Up.
up 5. I should have made that minus 5. That would have been a lot smarter. But okay, whatever. Flip it over the y-axis. All of a sudden becomes exponential decay. And then move it up 5. Let's do red. And the only point still on there probably is that one. So I'll be smarter when I write quiz questions. Ish. Is everyone okay with that?
Could it be a negative 5?
Oh, I mean, what I should have done is made it minus 5 so that we shifted it down and it actually fit on the grid that I gave you. Does that make sense? That was what I meant by that.
We can label it however, so you can draw.
Oh, yes, you're true, right. If you relabel my x and y axis somehow, and then you know, that's okay. Just you have to make sure you make it clear that you've done that. Like you could say, okay, well, all of a sudden I'm going to decide the x-axis at the bottom, and the y-axis is that, like, in the middle still. You could define this thing to be the new x-axis, and you could say that one stupid one you drew is not the x-axis. Goodbye. That's the point. But if you use the x and y-axis as they're given, you do have to draw it that way. My bad. Okay. Okay. The book asked you to use a graphing device, but because we know how to use natural logs, I thought that was better. But one way to solve this is you could graph e to the x and 1,000 and look for where e to the x is bigger than 1,000. Or you could graph e to the x minus 1,000 and look for where that's bigger than or equal to 0. This probably is easy, or why did I make that equal to? That was a boo-boo. And you need to get smaller. Okay. You could graph this, right, and look for where does the e to the x shifted down 1,000, where does it cross that axis? But I think a better way to do this is to just know how to undo the e function. So what is the opposite of x cubed? Cubed root x. What is the opposite of x squared? What is the opposite of e? ln x, which you're supposed to have seen at some point in time. So you can natural log this side and natural log that side. And that gives you just x bigger than natural log of 1,000, whatever that is. And ln of 1,000 is approximately 6.908.
Does log have a
Yep, so if you have regular log x, it's the opposite of 10 to the x, which is the topic of the next lesson. But e and ln are the special pair that you probably see the most, so you probably get a good familiarity with them. Okay, and 2 domain questions, then we get to do inverse functions, so woo! Okay, so find the domain of these functions. Well, does the numerator cause problems? Nah, right? Numerator can be whatever it wants. Who's causing problems here? The denominator. We need to figure out where that is equal to 0. I think it's true at 1. I'm going to do a little bit more solving, but that is correct. That's the same thing as saying 1 equals e to the 1 minus x squared. Does that make sense? And what power has to, what does this stuff inside the e have to equal for e to the power to be 1? Stuff inside has to be 0. So 1 minus x squared has to equal 0. And that's because e to the 0 is how you make 1, right? And so solving that, you get 1 equals x squared. X equals plus or minus 1. So those are the two numbers you have to exclude. X can't equal plus or minus 1. So in an interval notation, that's minus infinity to negative 1, union negative 1 to 1, union 1 to infinity. And once we know the content of the next section, we'll know another way to solve that would involve one more step using ln on both sides. Ln of 1 is 0. So we'll get there. Root e to the x minus 2. Okay, so do you buy that e to the x minus 2 must be bigger than or equal to 0? The thing you're rooting must be positive or 0? Kind of like the one we just did in example 9, right? Add 2 to both sides. And which function is the opposite of e? Natural log. So ln e to the x bigger than or equal to ln of 2, so x. And you can just leave your answer as ln of 2. Don't need to get me a decimal. You can just say as an interval, ln2 to infinity is what's good. And the fact that everything is big, this is x's are bigger than that number means you're going to positive infinity. Had the inequality gone the other way, you would have had minus infinity. That lesson was short. I think that's it, right? You guys are too quiet. You can say yes.